This is your presenter Asloob Mudassar, and I am presenting slide number 74 of the course on laser physics. Question is, find expressions for absorption and gain coefficients for quantum well semiconductor. Moreover, what do you understand from the strained quantum wells? How are they useful as laser materials? Give a few words on the future forms of quantum well semiconductors. The answer is, let rho jk dk perpendicular gives the number of available transitions per unit area in the range from k perpendicular to k perpendicular plus dk perpendicular. So here we are defining the available number of transitions per unit area by rho jk multiplied by dk perpendicular. Since transitions only occur vertically, that is along the z direction, rho jk dk perpendicular also equals the number of states in either the valence band or conduction band in the interval dk perpendicular. So this term that we have defined, rho jk multiplied by dk perpendicular, actually gives you the number of states either in the valence band or the conduction band in the interval dk perpendicular. Thus rho jk is equal to rho k is equal to k perpendicular over pi. This is rho k is equal to k perpendicular over pi is what we have calculated in the previous slides. So here we are taking the data from this expression from the previous slide, and we are plugging in that value over here. So rho jk is equal to rho k is equal to k perpendicular over pi. You know that k perpendicular was defined on the xy plane of the quantum well semiconductor. Consider two energy levels E1 prime and E2 prime belonging to two sub-levels in the valence band and the conduction band for n is equal to 1 respectively. So you see that here we are using the word sub-levels. It means that these are the levels which are formed in the quantum wells of the valence band and the conduction band. And E1 prime is the energy of a state in the valence sub-band, and E2 prime is the level of a state in the conduction sub band, and that band that we are talking about is the n is equal to 1 band, that is n is equal to 1 sub levels of the valence band and of the conduction band. For the valence band we are associating an energy E1 prime to the n is equal to 1 sub band in the valence band, and we are associating an energy to the state E2 prime in the conduction band, in the sub levels of the conduction band. The E2 prime minus E1 prime is equal to h nu naught is equal to E naught, where E naught is expressed as E naught is equal to Eg plus h bar square k perpendicular square over 2 mr plus delta E1. So to explain this further, consider the value of delta E1 given over here. That is delta E1 is equal to EC1 plus EV1. So you are measuring the energy from a state in the valence band to the top of the valence band, that is E1V is the energy in the valence band, plus you will add up the energy of the band gap, which is Eg. So E1V plus Eg plus E1C will give you the energy in the conduction band, and h bar square k perpendicular square over 2 mr is the energy of the electron in that state. So we have given that one, we have given that name as E naught, because E naught is actually the energy that is required to raise the electron from the valence band in the state with energy E1 prime to the state E2 prime. And we have represented that states also with energies E1V and E1C. E1V and E1C are actually the values of that level, that is n is equal to 1 level in the valence band, and E1C is equal to the energy of the n is equal to 1 sub level in the conduction band. So we are summing up these energies E1V plus E1V plus EG plus E1C, and then we are summing up the energy of the electron in that sub band of the conduction band, which is given by h bar square plus k perpendicular square over 2 mr. So where mr is a reduced mass, and delta E1, as I said, that delta E1 is equal to E1C plus E1V. The density of states in E0 coordinate can be written as, so you see that we have represented the density of states over here. For example, rho j k d k perpendicular, this is what we have defined, and we have said these are the transitions per unit area, and these also provide you the number of states in either the valence band or the conduction band. So here we are talking about, in precise words we can say that these are the number of states in either the sub levels in the valence band or the sub levels in the conduction band in the interval dk perpendicular, that is from k perpendicular to k perpendicular plus dk perpendicular. So now we are writing this expression in terms of the energy, that is the density of states in terms of the energy, which is rho j E naught multiplied by d E naught is equal to rho jk multiplied by dk perpendicular, and we have the value of rho jk, which is equal to k perpendicular over pi, and then multiplied by dk perpendicular. So this is the same thing, that is the number of states in terms of energy E naught and also in terms of the wave number k perpendicular, and we have specified the value of rho jk, which is equal to k perpendicular over pi. So if we get the value of rho j E naught, that is equal to, that is given by k perpendicular divided by pi multiplied by the derivative of dk perpendicular over d E naught, and this dk perpendicular over d E naught can be calculated, and we have also calculated this one previously in one of the previous slides with a value of 2 mr over h bar square multiplied by 2k perpendicular. So this is what we have calculated earlier, and you can also calculate it from this expression, that is from equation number 1. Just take the derivative of dE naught over dk, and then take the reciprocal of the quantity on the left hand side and also on the right hand side to find the expression of dk perpendicular over dE naught, and then substituting that value over here, which is equal to 2 mr over h bar square into 2k perpendicular, and that will give you the total value. So simplifying this expression will give you on the rightmost side, that is equal to mr over pi into h bar square. This is the value of rho j E naught. Density of states with respect to transition frequency nu naught, that is rho j nu naught, can be found from. You see that we have given the density of states with respect to the transition, with respect to energy in equation number 2. Now we are going to compute the density of states with respect to the transition frequency in E nu naught. Before that we have given in terms of E naught as shown in equation number 2. Now we are going to calculate the same thing in terms of the transition frequency nu naught. That is, we want to calculate rho of j nu naught, and the relationship is rho j nu naught into d nu naught is equal to rho j E naught multiplied by d E naught. So now we are relating, we are having this relationship, and from this relationship we can find out the value of rho j nu naught, which is equal to rho j E naught and multiplied by d E naught over d nu naught. Now this derivative, that is the derivative of E naught with respect to nu naught, can be computed from this expression, that is E naught is equal to h nu naught. So if you take the derivative of this, the derivative of d nu naught, of the derivative of E naught with respect to nu naught, that is d E naught over d nu naught, you will get that derivative equal to h. So putting that value over here, that is d E naught over d nu naught equal to h, we have this expression, and the simplified version is 4 pi into mr over h. This is given, this is shown in equation number 3. So rho j nu naught is equal to 4 pi into mr over h. So this is what we have represented the density of states in terms of the transition frequency nu naught in equation number 3. For the case of a bulk semiconductor material, the absorption coefficient was found to be. So you see that now we are specifying for the bulk semiconductor material, which we have already calculated, and for that one the absorption coefficient was alpha equal to 2 pi square over 3n epsilon naught ch multiplied by nu, that is the frequency of the beam, multiplied by absolute square of mu, which is electric dipole moment over here, and then the rho j of nu multiplied by, within parentheses we have fv of E1 prime minus fc of E2 prime, where you see that rho v of E1 prime is the probability that the state E1 prime in the valence band is occupied, and fc of E2 prime gives you the probability that the state E2 prime in the conduction subband is occupied. So here both E1 prime and E2 prime are related with the subbands in the quantum well of the valence band and the conduction band respectively. Now rho j of nu naught divided by Lz is the joint density of states for quantum well semiconductor. We have also defined the joint density of states in one of the previous slides. So rho j nu naught divided by Lz will give you the joint density of states for the quantum well semiconductor. To find the absorption coefficient for quantum well semiconductor, we replace rho j of nu in the above expression. You can see that rho j of nu is present over here. We are replacing rho j of nu by rho j nu naught divided by Lz for n is equal to 1 to n is equal to 1 transition. So these are n is equal to 1 to n is equal to 1 transitions mean that n is equal to 1 that is n is equal to 1 sub-levels of the valence band, and the transition from n is equal to 1 sub-levels of the valence band to the n is equal to 1 sub-levels of the conduction band. So this is what we mean from n is equal to 1 to n is equal to 1 transition. And you see that to find the what we are going to do is that we are going to replace rho j of nu by rho j nu naught over lambda z in the above expression, and finally we get this, that is alpha for quantum well semiconductor is equal to the same expression, except that we have replaced the above expression in the above expression rho j of nu was replaced by rho j nu naught over Lz. The rest of the quantities are the same, where E2 prime minus E1 prime is equal to h nu. That is the difference in these two levels in terms of the frequency of the incident beam will be equal to this, that is E2 prime minus E1 prime is equal to h nu. So for the case of absorption, you must provide a beam with this frequency so that you can make an excitation from the level E1 to the level E2 prime, where E2 prime and E1 prime are obtained from equation number 67.5 and 67.6. So here we are given the values of that E2 prime is equal to Eg plus E2, because we are now setting the reference at the top of the valence band, and from that one we are measuring the energies in the conduction band and the energies in the valence band. So the energy of that level in the conduction band measured from the reference set at the top of the parabola in the valence band is E2 prime is equal to Eg plus E2, and from that one the energy within the valence band will be measured negative, so E1 prime is equal to minus E1, and Ei is equal to h bar square k perpendicular square over 2 mi plus n square times E1i. This expression is also what we have derived in the previous slide, where I index can take the values I is equal to 1, 2. So if we are considering, for example, 2 levels in the valence band and the 2 levels in the conduction band, then this equation will hold for these two sub-levels in the valence band and the conduction band with I is equal to 1, 2. And E1i is equal to h bar square pi square over 2 mi into Lz square. So we have also specified the value of E1i. The gain coefficient for the quantum well semiconductor can be obtained from the gain coefficient for the bulk semiconductor material by replacing rho j of nu by rho j of nu naught divided by Lz, as we done for the previous case, that is for the case of absorption coefficient. Similarly, for the case of gain coefficient, we can similarly use an expression for the bulk semiconductor, and in that expression we can replace rho j of nu by rho j of nu naught divided by Lz. You know that Lz is the width of the quantum well, both in the valence band and in the conduction band. So G for quantum well semiconductor, that is the gain for the gain coefficient for the quantum well semiconductor, is given by minus alpha times the alpha QWS. So putting that value over here, we can write 2 pi square over 3 n epsilon naught ch multiplied by nu in the numerator, multiplied by the absolute square of mu in the numerator, and then multiplied by rho of j nu naught over Lz, and then of course we have changed the order because of the negative sign we have multiplied. So we have EC of E2 prime minus FV of E1 prime. Now you see that this gain coefficient for the quantum well semiconductor will grow, that is will be positive value, that is will be greater than or equal to 0, or at least will be greater than equal to 0 or equal to 0, would require that FC of E2 prime is greater than equal to FV of E1 prime. That is the probability that the state E2 prime in the conduction subband is greater than the probability that the state E1 in the valence band is occupied. Or equivalently, we can say that H nu is greater than equal to E2 prime minus E1 prime, and that is less than equal to in terms of the in terms of the E prime FC minus E prime FV. So you see that H nu must be greater than equal to this difference if you want to move the electron from the state E1 prime to the state E2 prime. So if you want to move exactly, if these states are sharp consisting of only one levels, then of course you need to provide H nu equal to this one. But if there are some more levels around E1 prime and E2 prime giving of you the same energy of transition nu naught, then H nu will be greater than or equal to E2 prime minus E1 prime, and this is given in terms of these energies, that is E prime FC minus E prime FV. So you see that for the conduction band to be occupied, we want that all the states in the conduction band should lie below the F prime FC. So this Fermi energy, which is E prime FC, is located in the conduction band, and the levels E2 prime is lying below this conduction band, so that this level could be occupied, and the probability should be higher for the occupancy of the level E2 prime. And this E1 prime which lies in the valence band, and this Fermi energy level, which is E prime FV, is lying in the Fermi level. And here the level E1 prime should lie above the E prime FV level, that is above the Fermi level, so that this level E1, this level is found to be empty level in terms of the Fermi level. So if this level E1 prime is lying below the Fermi level in the valence band, then of course this E1 level will also, E1 prime will also be occupied. So the simple rule is that if E1 prime and E2 prime are lying below the Fermi levels, below the corresponding Fermi levels, E prime FV or E prime FC, then of course these levels will have the probability to be occupied. For the transition to occur, H nu should be greater than Eg plus delta E1. because delta E1, you know that already we have mentioned that delta E1 actually includes E1V plus E1C, that is the energy corresponding to the level in the valence band and the energy corresponding to the level sub-level in the conduction band. So these two energies, this is what we are talking about, this energy over here, that is delta E1. So here we are writing this expression that H nu should be greater than equal to the band gap energy between the two levels, that is between the valence band and between the valence sub-band and valence conduction band. So this is Eg. So H nu should be greater than equal to Eg plus delta E1, where delta E1 is what I have mentioned just a minute ago. So here we can write the full expressions as that is H nu, that is the intensity of the incident beam, should have a frequency such that H nu is greater than equal to Eg plus delta E1, and should also be less than this F prime E prime Fc minus E prime Fv. So that these levels, that is we are talking about the levels for the absorption, that is for the movement of the electron from the level E1 to E2, so that these levels lie below these corresponding Fermi levels, so that they are definitely occupied and the transition could be possible. So that's why H nu should be less than this one. So ultimately H nu should be greater than this quantity, that is Eg plus delta E1, and at the same time H nu should be less than E prime Fc minus E prime Fv. This defines the gain bandwidth. You see that this H nu here, nu has a bandwidth which should be greater than the quantities on the left hand side and the quantities on the right hand side. So so this nu, so here H nu and particularly nu, which defines the bandwidth, should be greater than the quantity on the left hand side, which is Eg plus delta E1. And this provides you the lower limit of the bandwidth of the system, and the other quantities, which is E prime Fc minus E prime Fv, provides the upper limit of the bandwidth. So H nu, so the bandwidth lies between these two quantities, on the left hand side Eg plus delta E1, and on the right hand side, which is F prime Fc minus F prime Fv, that is the difference of the levels, that is the difference between the Fermi levels, Fermi energies of the two bands. So this provides you the bandwidth. So this defines the gain bandwidth as we have given in equation number 6. The transparency condition can be defined as, the transparency condition is that E prime Fc minus E prime Fv should be equal to Eg plus delta E1. So, and this is the condition when the material will behave as a transparent material. Because if you illuminate the semiconductor or the quantum well semiconductor material with any beam, then that beam will just pass through the material as if the material is behaving as a transparent material. Because under that condition, you see that this is the condition we have also discussed before in one of the slides. So this condition is actually the transparency condition for the quantum well semiconductors. Semiconductor material in 3 to 5 group have cubic symmetry. In the growth of quantum well semiconductors, we have a well material sandwiched between two similar non-well materials. For example, let me show over here. This in the middle, on the left hand side, we have the sandwiched material, which is the well material. And on either side of this one, that is on the top and on the bottom, we have a non-well material. So we are sandwiching a well material between the two identical non-well materials. So we have a well material sandwiched between two similar non-well materials. The materials are chosen to cover the desired range of wavelengths or the desired range of frequencies provided by this relationship. That if you want to set the width of set the gain bandwidth or the number of wavelengths to pass, or the range of wavelengths to pass through the materials. That is, you want to design your materials for that one. Then you need to choose materials such that you can set the gain of the material, that you can set the gain of these that you can set the material, or you can set the bandwidth of the material according to this expression. That is, you can set the gain bandwidth of the grown up semiconductor material using this equation. So this material, so the materials are chosen, that is the well material and the non-well materials are chosen to cover the desired range of wavelengths or the bandwidth of the system. The lattice constants of the non-well material should be equal to the well material in the quantum well plane. This produces a biaxial compression of the well material in its own plane. So let me show you the biaxial compression. You can see that the width of this well material, which is in the center, when these are grown together, then you can see that each cell in the well material is compressed from both sides, and you can see the narrowing width of these materials in the center. That is the material belonging to the well material. So this has been compressed from both sides, and this is called biaxial compression of the well material in its own plane, and a uniaxial tension along the direction orthogonal to the plane. So due to the uniaxial tension perpendicular to the plane, you can see elongation of these cells along the z direction perpendicular to the plane, and this arrow shows the direction of the plane, and you see that these are elongated in a direction perpendicular to the arrow that is shown, that is perpendicular to the plane of the material. So this is actually the caption is crystal lattice deformation during a quantum well growth in the 3rd to 5th materials. So here we have explained biaxial compression as well as uniaxial tension along the direction orthogonal to the plane. The equation has been shown in equation number 74.1, which I just showed you over here. And over here you can see that A naught, which is the well material before the process of growth, and after the growth you can see that A11 is actually equal to A naught. Here A naught you see that is greater than A1 is less than A naught, that is a compression, biaxial compression. So A1 is less than over A naught, and after having what biaxial tension, where along the orthogonal direction you can see that A12 is greater than A0. The material in the well then loses its cubic symmetry. So under the growth process, what happens is that the material in the well then loses cubic symmetry. This changes the band gap and also the effective masses within the valence band. The HH mass, which we called heavy hole mass in the quantum well plane, is greatly reduced approaching the electron mass in the conduction band. You see that we have also discussed a heavy hole parabolic curve of in the valence band. We have also discussed these HH you see that band, and the HL band and the LH band. We have discussed heavy hole and light hole bands in one of the previous slides. So please have a look on those slides so that you can understand the meaning of HH, heavy hole valence band. So we have heavy hole mass that is the mass of the electrons in the heavy hole, or for example, you know that when we talk about hole, it means that we are talking about the vacancy of the electrons there. So the mass of the HH mass in the quantum well plane is greatly reduced approaching the electron mass in the conduction band. This makes the density of states in the valence band to approach the density of states in the conduction band. So that is rho v, that is the density of states in the valence band, is approximately equal to the density of states in the conduction band. And this is what we have explained, that as a result of the formation of the material, as the result of the formation of the quantum well material, this happens, that is the HH mass in the quantum well plane is greatly reduced and approaching the electron mass in the conduction band. This makes the density of states in the valence band to approach the density of states in the conduction band, that is rho v, that is the density of states in the valence band is approximately equal to the density of states in the conduction band. The transparency density NTR, TR stand for transparency as a subscript. The transparency density NTR is greatly reduced, whereas the differential gain dg over dn is greatly enhanced, because you see that n is reduced in the denominator. So that's why the gain, the differential gain, that is the gain with the density, will be increased. So dg over dn, which is the differential gain, will be enhanced, because as a result of the formation, the requirement for the transparency density NTR is reduced. This happens when the mass of the holes in the valence band becomes equal to the mass of the electrons in the conduction band. That's mv is equal to mc. The strained quantum well semiconductor has the following advantages, being laser materials. Number one, a reduction in N transparent, that is the transparency density. The requirement of the transparency density is reduced. This lowers the threshold current density JTH. TH stands for threshold and J for the current density. So you see that when the density of the transparent material is reduced, then of course the current density, that is the threshold value for the current density, is also reduced. The second is that a reduction in NTR. A reduction in NTR, that is the reduction in the transparency density NTR, lowers the radiative decay rate, because the radiative decay rate, which is 1 over tau r, is equal to B times N. So if the condition on N is that N is reduced, then of course that also reduces 1 over tau r, that is the radiative decay rate is also reduced, and the Auger rate, which is defined as 1 over tau A, is equal to Cn square. So if N is reduced, if the requirement of N is reduced, then of course 1 over tau A, which is the Auger rate, is also reduced. So which in turn also lowers the value of the current density, the threshold value for the current density. So J, because J threshold is proportional to 1 over tau. So if the 1 over tau are reduced, then of course the J threshold is also reduced. The third point is that increase in differential material gain, as we have explained over here, that is the differential gain dg over dn will increase. So the increase in differential material gain is an increase in differential model gain. So differential model mode, you see, that means that different frequencies, emission of different frequencies. So you see that with the density, that is the differential model gain will also increase. This in turn decreases J threshold and enhances the laser efficiency. So because we need less, because our systems are working with reduced value of J threshold, that's why the laser intensity will be improved. So you see that we have discussed how the quantum well semiconductors are useful. That is, a reduction in the transparency density NTR is useful in order to improve the efficiency of the laser beam in the 3 steps that we have just mentioned in step number A, step number B, and step number C. So these 3 steps will improve the efficiency of the laser system, and in fact these 3 systems are guided by the reduction in the transparency density NTR. Since this is our last lecture of the semiconductor materials and also on the quantum well semiconductors material, so for the completeness I am adding some paragraph over here, although this may not be required in the question asked. So for completeness, a few words on quantum wires and dots are presented. In quantum well semiconductor, one dimension of the semiconductor material is made comparable to the de Broglie wavelength. So you see that I have discussed quantum well semiconductors in the last 3 to 4 slides. So in that slides we are making one dimension of the quantum well comparable to the de Broglie wavelength. In quantum wire, 2 dimensions of the semiconductor are made comparable to the de Broglie wavelength, whereas in quantum dots all the 3 dimensions are made comparable to the de Broglie wavelength of the electron. As far as the laser medium is concerned, quantum wires and dots will perhaps be used in the form of planar arrays of quantum wires or quantum dots. So here you can see that, let me repeat, as far as the laser medium are concerned, quantum wires and dots will perhaps be used in the form of planar arrays of quantum wires or quantum dots. However, there is a little success in the field due to technological challenges in producing satisfactory materials. Once the technical challenges are overcome, semiconductor materials of still lower threshold, higher differential gain, and narrower bandwidth will become available. So again, you see that these things, if happens, will further improve the quality of the laser beams, because the use of quantum wires and quantum dots will further improve the efficiency of the semiconductor lasers. So this is the end of slide number 74.